Welcome to Chapter 3 of the Chemoinformatics Introduction series. In this lecture, we'll explore how to navigate the vast universe of possible molecules. We'll learn to measure molecular similarity, visualize compound libraries in 2 dimensions, and select diverse molecules for screening. These skills are essential for drug discovery, where we need to efficiently explore chemical space to find new therapeutic candidates. Chemical space is the theoretical space containing all possible molecules. The numbers are staggering. Estimates suggest there are 10 to the power of 60 possible drug-like molecules. That is more than the number of atoms in our entire solar system, which is around 10 to the power of 57. Yet we have only characterized a little over 100 million compounds. Think of it like exploring the ocean with a teaspoon. Different regions of chemical space contain different molecule types. Approved drugs occupy a small but valuable region, natural products span a diverse area, and synthetic compounds cover yet another territory. The challenge of drug discovery is finding the right needle in this impossibly large haystack. How do we measure if 2 molecules are similar? We use similarity metrics applied to their fingerprints. The most common is the Tanimoto coefficient, which measures the overlap between 2-bit vectors as intersection divided by union. Dice coefficient weights the intersection more heavily, giving higher values for the same pairs. Cosine similarity treats fingerprints as vectors and measures the angle between them. Euclidean distance measures the straight-line distance between fingerprint vectors. Take aspirin and salicylic acid, 2 closely related molecules. With Morgan fingerprints at radius 2 and 2048 bits, Tanimoto gives 0.45, Dice gives 0.62, and cosine gives 0.63. Same pair, same fingerprint, 3 different numbers, so never carry a threshold from one metric across to another. For molecular fingerprints, Tanimoto is the gold standard because it handles their sparseness well. Let's understand the Tanimoto coefficient more deeply. The formula is the size of the intersection divided by the size of the union of 2 fingerprint bit sets. Visually, it asks what fraction of the combined bits are shared. One thing to keep in mind, a Tanimoto value only means something once you say which fingerprint produced it. All 3 examples on this slide use RD-Kit Morgan fingerprints with radius 2 and 2048 bits, that is ECFP4. Ibuprofen and naproxen, 2 nonsteroidal anti-inflammatory drugs from the same class, score 0.42. Aspirin and caffeine, which share little beyond a ring and a couple of carbonyls, score only 0.09. Glucose and cholesterol, structurally unrelated, score 0.06. So with ECFP4, values above roughly 0.7 mean very similar. 0.4 to 0.7 means the same chemical class, and anything below 0.2 means unrelated. The familiar rule of thumb that 0.85 means very similar comes from daylight path fingerprints, not from ECFP4, so do not carry that threshold across fingerprint types. With molecules represented as high-dimensional fingerprints, how do we visualize them? We use dimensionality reduction techniques. PCA, principal component analysis, finds the directions of maximum variance and projects data linearly. It's fast and preserves global structure, but may miss nonlinear relationships. TSNE, T-distributed stochastic neighbor embedding, excels at preserving local structure, making clusters very visible. However, it's slow and distances between clusters aren't meaningful. UMAP, Uniform Manifold Approximation and Projection, offers the best of both worlds. It preserves both local and global structure and runs much faster than TSNE. For exploring compound libraries, I recommend starting with UMAP. Once we can measure similarity and visualize chemical space, clustering helps us organize molecules into groups. K-means is the simplest. You specify the number of clusters K, and it finds circular cluster boundaries. It's fast but requires choosing K in advance. DBSCAN is density-based, finding clusters as regions of high density separated by low density regions. It handles arbitrary cluster shapes and automatically identifies outliers. Hierarchical clustering builds a tree of relationships, showing how molecules group at different similarity thresholds. A common workflow is to cluster a compound library, then select one or two representatives from each cluster for testing. This ensures diverse coverage of chemical space. Virtual screening is the application of these techniques to find drug candidates. Imagine starting with a database of 10 million commercially available compounds. First, we apply property filters like Lipinski's rules, removing 70% of compounds that are unlikely to be drugs. Next, we search for similarity to known active compounds, keeping the top 10% most similar. Then we score the remaining compounds using docking or machine learning models, prioritizing the most promising hits. The result: from 10 million compounds, we identify perhaps 100 high-quality hits for experimental testing. This funnel approach makes drug discovery tractable by focusing expensive experiments on the most promising candidates. Lipinski's rule of 5 is a famous filter for drug likeness, derived from analyzing orally active drugs. There are 4 criteria: molecular weight 500 or less, log P 5 or less, meaning not too greasy, hydrogen bond donors 5 or less, and hydrogen bond acceptors 10 or less. The name comes from the thresholds all being multiples of 5, not from there being 5 rules. Aspirin passes all 4 comfortably, with a molecular weight of 180, a log P of 1.3, 1 donor and 3 acceptors. Cyclosporin A is the classic exception. It is a cyclic peptide of 11 amino acids with a molecular weight of about 1,212 hydrogen bond acceptors, so it fails 2 of the 4 criteria outright, and yet it is given orally because internal hydrogen bonds fold the molecule up and hide its polar groups. Modern approaches go beyond the rule of 5. Weber's criteria add rotatable bonds of 10 or less and a topological polar surface area of 140 or less. PAINS filters remove problematic substructures, Brank alerts flag toxic groups, and QED provides a continuous drug likeness score. When selecting compounds for screening, we want maximum chemical diversity to cover as much chemical space as possible. The max-min algorithm is elegant. Start by picking a random compound, then repeatedly select the compound that is most distant from all previously selected compounds. Specifically, for each candidate, calculate its minimum distance to any selected compound, then pick the candidate with the maximum of these minimum distances. This ensures each new selection adds maximum novelty. Compared to random selection, max-min provides much better coverage of chemical space. It's widely used in compound library design and hit expansion campaigns. Let's recap what we've learned. Chemical space is the vast universe of possible molecules, far larger than we can ever fully explore. Similarity metrics, especially the Tanimoto coefficient, let us measure how alike 2 molecules are. Visualization techniques like PCA, TSNE, and UMAP help us see patterns in high-dimensional data. Virtual screening combines property filters, similarity search, and diversity selection to efficiently find drug candidates. In Chapter 4, our final chapter, we'll explore reaction prediction and retrosynthesis, how to predict what reactions will make a molecule and plan synthetic routes. Try clustering your favorite class of drugs to see how they relate. See you in the next chapter.